Hello there. Last time we started discussing how to obtain the dynamic response of a continuous system, and we are going to be continuing today to be talking at dynamic response for continuous systems. Okay? And just to kind of lay down the specific steps. This is the steps in the modal superposition method. Okay, the steps. What is step 1? Well, write the governing equations of motion and identify appropriate boundary conditions. This is the first step. Okay? Today in the later part, after I have written this, we're going to see how you can develop the governing equations. What we have done is we have developed the governing equations in two situations. One is a beam in a simple beam in axial deformations. We have developed that equation of motion, and we have also developed the equation of motion for simple flexure. In the later half of today, we are going to be developing for another type of beam, writing down the equations of motion and also seeing what should be the corresponding boundary conditions for it. Okay? So therefore, that is the first step. The next step is really so in other words, get the frequency equation, then derive omega n and phi n x. Okay, in this particular case, we are talking about beam, so it is always phi n x. Okay, so that's step 2. Then step 3 is writing down the computing generalized mass and loading. How do you do that? Well, Mn is equal to integral 0 to L phi n squared x into m bar x dx, that is Mn, and Pn is equal to 0 to L phi n x p bar x upon t dx. Okay, and once you've found out for all n, once you've done that, the fourth step in the process is to solve the modal coordinate equation, which is what one? M n y n double dot plus k n y n dot is equal to P n, where k n is actually omega n squared m n. Solve this. There is a single degree of freedom. Solve this for y n of t. Solve it for y n of t. Then step 4 is not step 5 is nothing but evaluate displacement response. Okay. For example, either u x of t or v x of t is equal to n equal to 1 to infinity phi n x y n of t. So, you have got phi n, you know phi n x, and you can get that. So, that gives you your evaluate displacement response. What is the next step? Well, you have evaluated displacement response. The next step is to evaluate. So, step 6 is to evaluate force response. For example, axial deformation, P of x is equal to E A del u by del x. So, now since you have got u x of t, del u by del x into E will give you P x of t. Okay. And then if you have flexural deformation, then moment m x of t would be equal to E I into del squared v by del x squared. Okay. So, you can evaluate the force response, and that is it. So, these are your dynamic analysis for a continuous system. First step, write down the particular equation of motion and the boundary conditions. Second step, you find out solve the free vibration problem and obtain omega n and phi n of x. The third step, well, evaluate the generalized mass and loading, which is m n and p n, and m n is equal to integral phi n squared into m bar x dx, and p n is equal to integral over the whole length phi n into p bar x of t dx. Okay? And that is what your system looks like. Okay? So, now let me, I will solve some examples. I mean, I will solve examples for both flexural response and thing. But I just like to say one particular thing, and that is P n into phi n. This is, by definition, this is a load intensity for continuous loads. Okay? Now, suppose you have a situation where, let us say, if it was like this, let us say, if it was this, say UDL, then this would become a constant, and that this P bar would be omega W. Okay? And that is no problem, you can do that. Now, suppose on the other hand, you have let us say a load like this, a concentrated load of P. How would you solve this problem? Well, there are two ways of solving this problem. Writing this as a continuous, and then the P bar x t essentially becomes P of t direct x minus L over 2, where x starts from this. This is like, let us say, L over 2, L over 2. Then direct function. A direct function is nothing but a value that is 0 for every value which is not x not equal to L by 2, and it is an infinite value at. So, that when you integrate it over the whole length, all you get is, when you integrate, like let us say phi n into P of t Dirac x minus L upon 2, what you get is P over t times phi n x equal to L over 2. This is what you get. Now, note this, what is this? As long as you understand that the basic concept in Pn mode is what? In a way, it is the work done by the load. As long as you remember that, you see, what is this? Pn into the phi n x of t. Suppose, for example, I had a situation where I was to say this, that look, I had a applied moment at L by 2, then what would be Pn in this particular case? Well, obviously, in the same procedure, this would be equal to m of t into phi n prime at x equal to L by 2. So, you understand the point? The point that I am trying to make is that in this P bar phi n is essentially for load intensity for continuous load. So, this defines the load intensity, and of course, if you have a continuous load, you can always define it in this fashion. Okay? And the other way to do it is P bar, if it is m of t, it would be d prime x minus L over 2, which is that the slope at particular point. Okay? So, these are issues that we can always handle as long as you realize that even for continuous systems, the load Pn really is in terms of being a particular work done in a particular sense. So, as long as you understand that, there are no issues associated with this particular problem. Okay? Now, what I would like to do is, so that gives you an overview of dynamic response. In the next lecture, I am going to actually solve some specific problems maybe towards the end of this lecture, I will define some of the problems that I will talk, but I will take it up in the next lecture of actually solving some problems both for axial deformations and flexural deformations, just to give you an idea of the procedure, the steps that I have given you. This we will need to put it down. Okay? So, but before I go into those, let me look at a particular problem that I had talked about, and that is, remember the case where we only looked at flexural deformations of simple beam, and we got the thing as d upon dx squared ei del squared v by del x squared plus m bar d squared v by dt squared is equal to p bar x of t. This was the equation that we wrote down for a flexural beam. Now, in this particular case, this was where we considered only flexural deformations. Okay. In other words, if you looked at this, and the relative motion, okay, the relative motion of this was let us say that the slope alpha was the same as the slope of the neutral axis. Okay, and that is the reason why we could say that the curvature is directly this. So, it is only flexural deformations, and also we only took the fact that the beam was not deep enough for there to be. So, the beam was like a point mass, so that it only had cross section as point mass. These are the assumptions that we made in deriving this. Now, by and large, this is okay for normal beams, but suppose we are tackling the flexural deformations of a chimney. A chimney would typically be exceedingly large in dimension, and therefore, it could not, if it is a very large dimension cross section, then it is very difficult to consider it as a point mass at this thing. There is also something called rotatory inertia. So, when you have a large dimension cross section, large dimension cross section, and this is your neutral axis, it is very difficult to say that look, this entire mass is concentrated at this point. So, in such a situation, you have rotatory inertia. Rotatory inertia is one in which if a cross section rotates, then there is if it rotates in this direction, there is a MI set up, which is a moment of a moment of inertia. It is called the moment of inertia. So, a moment of inertia comes up, and this is something that we have to take care of. And similarly, if you have a cross section which is deep, the beam is deep. A deep beam is one where L is typically less than 10 d. If L is less than 10 d, the beam is called it is not called a slender beam, it is called a deep beam. And if you have this, then shear deformations cannot. So, large cross section rotator inertia cannot be neglected, and here if L is less than d and you have a what is known as a deep beam, shear deformation cannot be neglected. So, typically what happens is that in this particular case, we only had the equation that we looked at, the flexural deformations, in fact the flexural motion of a simple beam only had flexural deformations and linear inertia term. Now, if you have a deep beam, you not only have to consider the shear deformations, but you also have to consider rotatory inertia. So, the question then becomes is how do I generate the equation of motion where I consider both flexure and shear deformations and rotatory inertia. So, this is this, and typically this beam in regular parlance is called a Timoshenko beam. So, how do we solve this particular problem. Okay. So, now let us look at this situation. What we have is that let us look at the neutral axis and the cross section. Now, under flexural deformations, okay, what we have is, look, the neutral axis itself rotates. Okay. So, and we know that this, okay, which is the relative, it is the relative motion of the, if you have a length dx, let us just take a length. Okay. So, this length is dx, the rotation of this end relative to this end, okay, slope is equal to dv by dx, or I will call it del v by del x, because after all v is a function of x and t, and so it is del v upon del x. Now, in addition to this, what happens is, so you have a situation where this goes like this and this is like this. In addition to this, if you take shear deformation, then what you have is that this part rotates, this part rotates relative and to this, and so this is known as beta, which is the shear distortion. This is the distortion of the thing. And note that after all, if you look at this motion relative to this motion, these two together is alpha, which is the rotation of cross section. So, what you have in this particular case is the following, is that in this particular case, if you look at this is the slope, that is the slope of neutral axis. Okay. So, this is the slope of the neutral axis, this is beta, and what we have is rotation is alpha is equal to beta plus del v by del x. This is the kinematics of the cross section. Okay. Now, if I look at the equilibrium, so this is the kinematics. Understand that what I have done over here is the kinematics of the cross section under both flexure and shear deformation. Now, let us look at the equilibrium. We have looked at the kinematics, let us look at the equilibrium. The equilibrium says the following. Remember that everywhere you have to satisfy kinematics, you have to satisfy equilibrium, and you have to satisfy the force deformation relationships. Okay? So, let us look at equilibrium. If I look at equilibrium, this is what happens. These are the forces acting on the body. M, this is m plus delta m by dx into dx. This is length dx. So, I am looking at the equilibrium now. So, this is there. Then I have v, I have v plus del v by del x into dx. I have the load, which is p bar. Okay. In addition to that, if I look at this as the neutral axis, I have, because if this is the motion, okay, then I have what is known as f I. In addition, since this is the rotation, there is going to be a m I. Okay. So, these are all the forces acting on the body. Okay. Now, what is F I? F I is equal to m bar dx into v double dot x of t. This is what you have as F I. And what is m I? The moment is given by rho, which is this thing, into I, which is the mass moment of inertia, rho into I. So, rho is the density, I is the moment of inertia of the system, okay, into, so this one is actually del squared by del t squared. So, this is the linear, and this one is the rotation. See, if your entire cross section is going by alpha, then this is d squared alpha by d. So, if you look at this, this is equal to m bar I upon a del squared alpha, and I upon a is what? Radius of gyration squared, right? We have already seen that. So, this is equal to m bar r squared del squared alpha by del t squared, where alpha is the rotation of the cross section, is the rotation of the cross section. Okay. So, therefore, this is the total rotation, because ultimately the mass only sees the rotation. It does not see how much the neutral axis moves by, etc., etc. Okay. So, these are your F I into m I. Okay. F I and m I. Let me write down first my equilibrium equation for moment. So, if I were to write down the equilibrium equation for the moment, okay, so that means summation moment is equal to 0. What do I get? I get m plus m I. Okay. Now, this m I into dx, of course, because this is only at a particular point. Then what else do we have? We have the remaining point, which is dv, v into dx. I am taking moments about this particular point, okay, v dx, right, and then I have minus. So, this one I have taken this as positive, minus m into del m by del x into dx, the entire thing is equal to 0. This is my equation, and so if I rewrite this, what I get is dm by dx is equal to v plus m bar r squared into del squared alpha by del. This is the angular acceleration. So, this is my first equation. Okay. So, this is going to be equal to del v del x, okay, plus f I, this is summation moment force is equal to 0, is equal to del v plus f I minus p bar is equal to 0. Okay. So, now this can be rewritten as del v by del x, f I is equal to m bar dx, okay, into del squared. So, this is going to be equal to minus m into del squared. Now, this one is going to be equal to del squared v upon del t squared, okay, plus p bar x of t. This is my second equation. Okay. Now, let us look at certain aspects, and that is these are what are known as the moment. I mean, you have to have two relationships. You have one is the relationship for V and one is the relationship for M, and these are the force deformation relationship. So, according to definition, okay, V is equal to K prime G A into beta, where if you look at it, sorry, I will rewrite this as K prime A into G into beta. This is nothing but what is known as the cross-sectional shear area, okay, where K is a shape factor, okay, and this can be found out for anything. For example, for a rectangular cross section, K bar is equal to 5 by 6. This is something that we know already, okay, from structural analysis. So, I am just rewriting it. Okay. So, V is equal to K bar G A beta, where beta is the shear distortion. So, in a way what we are writing is shear force is equal to area into G, G into A is like a force into the distortion, angular distortion. Okay. So, that is what V is, and the other one is is essentially what we have as M is equal to EI, and this is where it is a little bit interesting, and that is EI into the rate of change of rotation. Is the rate of change of rotation of the cross section, because M is related to the rate of change of acceleration, cross section. So, this is this, okay, and of course, here the major fact that comes in is that you have a situation. So, now if we go back to our that moment equation here, this particular equation, okay, I can rewrite it in this fashion. I can rewrite it in this particular fashion, del by del x into m. So, m is d alpha upon dx, okay, is equal to V. V is nothing but K bar A G into beta, okay, and plus m bar r squared del squared alpha into del t squared. This is what this equation lands up being by substituting these two, the V and the so we are incorporating the force deformation relationships into the moment, the equation that we got from the moment equilibrium. Okay. Now, note very interesting that there seems to be two terms, one alpha and one beta. Okay. Now, this but we know that fact that actually beta can be written in terms of alpha delta in this fashion. Remember, alpha is equal to beta plus del V by del x. So, beta is equal to alpha minus dV by del x, where V is this. So, this relationship exists. So, you can actually plug it in here, and this equation then becomes nothing but this. This equation becomes del by del x EI del alpha by del x is equal to K prime A G into alpha minus del V by del x plus m bar r squared del squared alpha by del t squared. Now, you know, understand this equation, I would like to write it in terms of v. So, I need to find out del alpha by dx in terms of v some way. So, how do I do that? Well, let me look at the equation that I got from my which we had got it as del v by del x is equal to p minus m bar del squared v by del x squared. Now, what is del v by del x? Del v by del x is nothing but the v is this. So, therefore, what we get is del of k prime a g alpha minus del v by del x, that is v, is equal to p bar, sorry, that is p bar minus m bar del squared v by del t squared, okay, sorry, del by del x. Now, let us assume for now that this can be actually taken forward, but let me just assume that EI, this is a uniform cross section, okay. Otherwise, I would have to put it down in some format. But the point that happens is, if we take it to be, I can actually derive it in another way, but suppose I take it to be uniform cross section, then what happens is EI k prime a g m bar r squared, okay, all are constant. If that is the case, then what do we get? We get this particular situation. The bottom equation becomes what? It becomes k prime a g into del alpha by del x minus del squared v by del x squared is equal to p bar minus m del squared v by del t squared. So, in other words, if I just put it this way, I get del alpha by del x is equal to del squared v by del x squared plus 1 upon k prime a g into p this gives me del alpha by del x in terms of v's, only v's. Okay? So, what I need to do now is that I have got this equation. Remember, I have got this equation, I have got this particular equation. In this, I have one d alpha by dx, okay, and the other one that I have is that I have an alpha here. So, what I need to do is I need to just differentiate throughout by differentiate by dx. So, if I put that in, what do I get? This particular equation, if I put it, if I differentiate it twice, once with respect to x, what I get is the following. I get d squared by dx squared into EI del alpha by del x is equal to k prime a g into del alpha by del x minus del squared v by del x squared plus m bar r squared del cubed alpha by del x del t squared. This is what we get. Now, in this particular case, you substitute the fact that d alpha by dx is given by this term. Okay? If you substitute this into this equation, what you ultimately get is the following. Okay? Now, in this particular case, this becomes del squared x by del x squared into E I, and this del alpha by del x, let us just substitute it, you get it equal to del squared V by del x squared plus 1 upon k prime A g into p bar minus d squared V by dt squared. Okay. Then what do you have here? Then you have this then is equal to, now this one, if you look at it, is equal to nothing but p bar minus m del squared V by del t squared. Okay. And this one is m bar r squared del cubed alpha. Now, so therefore, this one becomes, okay, this one needs to be looked at a little bit more carefully, dx dt squared. So, now this becomes nothing but, if you look at it, alpha has two parts to it. So, let us just go about it. Okay. Alpha has two parts to it, and therefore, this one essentially, if you rewrite this, this part becomes here, all of this comes out, and ultimately the equation goes in this format. I will just write the final equation, and I will explain what all of those terms are. There is one E I into del fourth V by del x fourth. That comes from the double difference, and E I is a constant. So, all we get is this is the fourth order term that comes. Okay. Then we have minus p bar minus m bar del squared V by del t squared. That comes from this part, okay, which is this part becomes just this. So, this part is what I put on the other side. So, if you look at this part is the elementary beam case. Okay. Now, in addition to that, you have one term which is del fourth V by del x squared del t squared. This is the term that comes from this particular part, because you will see that this del alpha by del x has two parts to it, and that is it has this, right. So, this is nothing but, if you look at it, you can write it as d by dt squared of d alpha upon dx. This is what this is. Okay. So, if you look at this mr, this d cubed is nothing but d squared of d alpha by dx. And so, when you substitute d alpha by dx from here, you get one term which is just mr del squared V by del x squared, and this is del t squared. So, that is this particular term that you get over here. This is purely due to rotatory inertia. The other part that comes is E I upon k a prime g del squared by del x squared of p bar minus m dv. This one comes from the other part, and that is that if you look at this part, del alpha by del x has this part which is now also there in this part. Okay. So, this part is being taken care of. So, that one is EI upon KIG into this. This is purely the shear distortion part. Okay? This is purely the shear distortion part, and now you have another term which is this term being double differentiated. Okay? So, what you have is this term being double differentiated. So, what you have now is the following. It comes out as minus m bar r squared upon k prime a g del t squared into p minus m bar del squared v upon del t squared, and this whole thing is equal to 0. Now, if you look at this, what is this? This one, you look at it, is purely shear distortion. Okay? Because if this does not exist, if this becomes infinite, this disappears. Remember that if shear distortion is to be neglected, you are to assume that k prime a g is infinite. If this is infinite, this goes to 0. Okay? So, this is purely shear distortion. This term, if r squared, okay, which is the rotatory inertia term, if that goes to 0, then this term disappears. But if you look at this term, it is a very interesting term. It has both m bar r squared, so it has the rotatory inertia part, and it also has the shear distortion part. So, this actually part is a combined shear distortion plus rotatory inertia. Okay? So, therefore, you have a very interesting situation that if I am going to rewrite this in its proper format, and if I rewrite this in the form that you are aware of, then this equation becomes, the equation of motion becomes the following: EI del fourth v upon del x fourth plus m bar del squared v by del t squared. That is the simple motion. Okay. Now, in addition, you have m bar r fourth d fourth dv squared upon, now this is a combination of what? The x squared gives you what? Because this is m bar into r squared, so that there is a square of distance. This part takes care of that distance. So, this, in other words, is the rotatory inertia purely. Okay. Then we have plus EI k prime a g into, well, this is, there is a minus term, m bar del fourth v into del x squared into del t squared. So, you see exactly the same, only this part is an additional part which comes from distortion. Okay. Then we have minus m bar r squared k prime a g into, so this is going to be into m bar del fourth v by del x squared this is del fourth into del t fourth. sorry, this is x squared. So, this is del x squared del t squared. Okay. So, this is another term is equal to, now I am putting every other term on the other side, and there I have p bar, okay, minus E I upon k prime a g into del squared p by del x squared and minus m bar r squared k prime a g into del squared p by del x squared. So, what we have here is the following, that we have a fourth order equation that reflects the distortion, the flexural energy. Then we have one term which reflects directly the linear term. The other three terms that you see are really also in essence a kind of a inertia, but in a slightly different manner. This part E I upon k prime is also a double this thing in terms of distance squared, and this is also distance squared. So, if you look at all of these, what you have is that this particular whole thing, this part basically becomes m bar into distance squared. So, that this part is just the distance squared. So, therefore, you look at this term, it is actually nothing but one part which represents like a massive inertia, rotator inertia term, and on the left hand side also, in addition to p bar, you also have terms which are d squared p bar by dx squared associated with it. One part with this again is a distance squared, and this is also distance squared. Both of them are distance squared, and therefore, left hand side, right hand side is nothing but a load term. Only thing is that this solution of this equation becomes that much more complicated, but nonetheless this represents an equation of motion where shear distortion and rotator inertia are included. Of course, the boundary conditions are going to be exactly the same. The only thing is here, please remember that if you have a simply supported beam, okay, you have phi prime and phi and moment. But remember, moment is E I del alpha by del x and not del v by del x. So, it does not automatically become, it becomes in a Timoshenko beam, there are no homogeneous boundary conditions, all boundary conditions are non-homogeneous. Okay. Thank you very much. I will stop here as far as the Timoshenko beam is concerned. For the next class, we are going to be solving problems from a variety of dynamic response for simple beams. Thank you. Bye-bye.